G'day everyone. So what am I doing with this potentially lethal looking 500 volt battery made out of a whole bunch of 9 volt batteries? Well, I'm calibrating an electrometer. I've been working away at the dry pile thing that I've been trying to build. So I need a way to measure the voltages out of the dry piles, which are at a very high impedance and very high voltage. With simple equipment. I've got some equipment that can do it. Obviously, a Keithley would be the ideal instrument, but it would cost a fortune. I'm doing it a whole bunch cheaper, using a little bit of ingenuity and maths. Okay, so what I'm going to do is I'm going to charge up one capacitor, a fairly high voltage, fairly small capacitor, using the voltage source of whatever I want to measure. Then I'm going to close this switch and dump the charge, equalize the charge between that capacitor and a larger capacitor that was shorted. So the voltage that the pair of these capacitors end up at is quite a simple expression here, based on the charge voltage over a capacitor, and then I can measure it with this JFET source follower. This JFET source follower, I'll show you in a minute, is something that I built to measure the individual cell voltages, but obviously it runs from 9 volts. It's limited in how far it can, basically its compliance and how much voltage it can actually take. So this simple capacitive division system, charge distribution system, lets me measure much higher voltages in the input by dividing it down using the ratio between these capacitors, or the ratio between one and their sum technically, but as long as they're relatively large, order of magnitude difference between them, it ends up being approximately, in this case approximately 100, it's actually 101, but then with the source follower there's some imperfections in that and a whole bunch of scale errors that eventually, when you work it all out, what I did is I calibrated it using a whole bunch of numbers. These ones were done with just the bench power supply up to about 60 something volts, and then obviously I wanted to calibrate it at a higher voltage, so I assembled this horrifying thing with a whole bunch of 9 volt batteries that I have here for the lab. So I'll show you how it works. Alright, so first of all, let's not electrocute myself doing this. As you can see, 502 volts, open circuit. The switches I implemented using reed switches. Reed switches are kind of a low leakage way of doing this. They work reasonably well. I haven't cleaned them. There is a little bit of residual leakage, as you'll see in a minute, but they're not doing too bad for sub half a kilovolt. So this switch is the charge transfer switch, and this switch is the zeroing switch, and I can just put a magnet near it to reset it, and not electrocute myself in the process. Alright, so that's zeroed now, as we can see, 0. Now I'm going to apply the 500 volts using the alligator clip here. I don't recommend you do it this way. May build something a little less of a lash up than this. So now I've charged it. As you can see, there's a little bit of leakage going on, and I'm going to have to fix that, but for now let's just ignore that. And then I close the switch using a magnet, and the charge is transferred between the two capacitors, and we see we get about 4.57-ish volts. And we looked at here, 4.563, 502, so it's a little bit, it's drifting down slowly as the gate leakage discharges the capacitor. Anyway, I put these numbers that I achieved with my power supply into a fitting algorithm, and I got K of about 113, 114-ish. I think if you do the math on these, it works out to be about 112, so that might be leakage. Could just be, slight non-linearities in the follower. But in any case, it's pretty good. It'll do the job to tell me whether or not the electrometer is, whether or not my dry pile is actually working properly. So, as a primitive electrometer, it'll do. Okay, so now that we've put the scary battery away, we can go back here to the bench and try it with some of these far less dangerous dry piles. So this is the first dry pile that I built. This has aluminium and manganese dioxide. Now I'm going to zero my little electrometer here, and I've already connected up the negative pole. I'll connect up the positive side to the capacitor for a few seconds. disconnect it, and then transfer the charge. See? 692 millivolts. Okay, so if I put that in here, in the calculator, multiply that by a scale factor, it's 78.79 volts. So, not exactly 400. Could it be that I didn't leave it to charge long enough? It's possible. Let's try it again. Okay, reset back to 0. Let it charge up for a little bit. So you can see here I've also got, this is a later cell, later dry pilot I built. This uses zinc and manganese dioxide plates, cells. It's got quite a bit better voltage per cell. So this is 400 cells. This is a bit less than 300, I think it's 260-ish. It should be 264, but I lost a few in the cutting. I managed to trash a few or drop a few on the floor or whatever. And this one here is one that I'm building right now that I added ammonium chloride. Oops, voltmeter went to sleep. I added ammonium chloride to the chemistry of the manganese dioxide side, which increases the cell EMF quite dramatically. I've only made 88 cells in this one so far, and we'll measure that one in a second. You can see here I've got a whole bunch of different test pieces that I made up, and I used the high impedance voltmeter that's part of this charge division, or I guess it's not technically charge division, it's more like a voltage division electrometer, a constant charge electrometer. It's kind of the reverse of those electrometers that they had back in the 1800s. So the first electrometers that could actually measure the output of voltaic piles. They were called a condensing electrometer. So you had one plate on top of the other with a thin piece of dielectric. Normally had little glass standoffs, or they'd coat one the plate that was attached to the leaves, the leaves that move apart when they're charged. They'd have that insulated, so they'd charge up the top plate, and then by grounding the bottom plate by induction, they'd charge the part with the leaves, and then you'd pull off the other plate. And as you separated the two plates, the voltage would soar because the capacitance would drop. It's the kind of the reverse of that, the V equals QC that we were talking about earlier. So if C drops and gets smaller, voltage is going to blow up. It's a very handy thing in the 1800s when we didn't have transistors and such to be able to measure extremely small voltages. They did have actually no, in the really early days they didn't have moving coil like Davazanals or whatever it is, movement meters. So they couldn't really do it any other way. I think eventually they ended up with a quadrant electrometer that was far more sensitive, but the condensing electrometer for a long time was the most sensitive electrical instrument. Anyway, so this thing's been sitting there, you can see it's leaked 32 millivolts. Wow, that's horrible. Okay, so let's do the charge transfer. Oh, I touched it. Well, that's terrible. So that's 1.095. About 124 volts. That sounds more reasonable. So we know that there was 400-ish plates in there. I might have miscounted one or two. So that's 310, 312 millivolts per plate, which is reasonable, for aluminium manganese dioxide cell that's been sitting here for a long time. Aluminium is notorious for forming an oxide layer, and I'm not entirely sure how bad that is for this sort of really high impedance cell. I know there's been some attempts over the years to try and use aluminium instead of zinc in batteries, and they've always had problems with aluminium oxide. I mean, they've done various things to the chemistry to try and improve that, but they haven't really been able to make a commercially successful battery using aluminium and zinc chloride or aluminium chloride, manganese dioxide kind of chemistry, or carbon zinc, carbon aluminium. Anyway, let's measure the zinc dry pile here. 0. Do this one a bit more quickly. This also has a lower impedance, so it can actually charge up the cell pretty quickly. Charge up the capacitor, the 330 picofarad capacitor here, so that should be enough. 1.13 volts. It's 128.6-ish volts, and we know that there was, what did I say, there was 88 plates per page, and there's a little bit less than 3 pages in there, so there's probably about 220 plates. And that's about 580, 590 millivolts per plate, which is, you know, getting better, certainly better than the aluminium one. So let's test the zinc and ammonium chloride one, even though it isn't fully compressed together here properly because I haven't got enough plates yet, and there's only 88 in there. Let's measure it. Okay, this is a little dodgy because it's not fully pressed. 0. Charge. Transfer. 535 millivolts. So it's 60.9 volts, and we know that there's 88 plates, so that's 692 millivolts per plate. It's 0.6.7 volts per plate was what the original dry piles used to get. So it looks like I've got the chemistry in the right ballpark. I can now go ahead and manufacture much larger number of plate dry piles, number of cell dry piles, and hopefully we'll be able to get, you know, kilovoltages out of these things. Now I also have the metrology sort of working so that I can measure the high voltages up to 500, or calibrate up to 500 volts. I'm obviously limited by the switches. These reed switches I think are only actually rated to 250 volts DC. They probably are a little bit better than that, but I probably want to build something a little less primitive than this anyway. Alright, so let's go and talk a little bit about the cell chemistry. Okay, so to measure the individual cell plates that are used for making these dry piles, I built this high impedance voltmeter. This is also the building block for the voltage division electrometer that you saw earlier. It's a source follower. I've just used a 2N5484 JFET, which is, you know, sort of an RF amplifier kind of FET. It's not really ideal for the job. It has a fairly low leakage, but it could be better. I probably should have used a PN4117 or you know, a more capable op amp. Even your average, you know, TL072 op amp probably would be okay, but there are better op amps. I didn't have them at the time. I've ordered some, and I rummaged through my junk box, and I managed to find one specimen of an LMC 662 CN. These are incredibly low leakage input MOSFET amplifiers. They have 2 femtoampere and like guaranteed 2 femtoampere leakage, input leakage currents. So these are truly magical devices if you want to build an electrometer or any kind of high impedance device. So ionization chambers, picoampere meters, leakage meters, you name it. They're super useful. And they're not particularly expensive either. I think they're $1.50 or something in bulk, but yeah, they're really cool, and I'll probably be building a less hacky instrument out of one of these, particularly a leakage meter, which would be particularly useful for some of the other experiments I need to do to make all this work. But anyway, what I have at the moment is the JFET voltmeter, and it works fine. There's a calibration table here, as you can see, that I've assembled because the source follower isn't exactly, you know, it doesn't have a voltage gain of exactly 1, so I fitted a line to it, and it compresses it about 8 volts. I wouldn't trust it above 7 volts because there's about a volt here on the source when it's shorted because of the VPP and the IDSS of the. Anyway, enough math aside, the source follower works pretty well. This pot here is the zeroing pot. It just sets the voltage the same as the source when the input is shorted. You should use a Surmet trimmer. I didn't use a Surmet trimmer, so it's incredibly touchy to try and zero it. Use a Surmet trimmer. The actual values are not that critical. This is just to make it somewhat less touchy and get it near 2 volts, I suppose, across this resistor, so it's near center. Anyway, this is just normal multimeter, voltmeter. You can actually put a moving coil meter in there if you want, but the impedance has to be, you know, something that the source follower can actually drive. Again, op amps, way better way to do it. This resistor is just to try and protect the port amp FET from getting blown up by ESD or general accidents. Input wise, this is the positive side, this is the negative side. I built the device physically on a peg, which allows me to clip it onto the cells. I'll show you. Okay, so here we have it. I socketed the FET on the off chance that I might actually get a decent FET at some point. The PN 4117 is very, very hard to get now. You can get the micro miniature PN, either the surface mount version of it anyway. So I guess I might be using that in the future. But this little hack works fine. Here's the pot for zeroing it. I've got copper PCB material plates here for grabbing onto the test plate. This is a 1 inch square-ish manganese dioxide on one side, aluminium foil stuck to the other side of the paper. We put it in, and we can see 750 millivolts or so EMF for the single cell. This is obviously loading it in the probably nanoampere kind of region, so even incredibly feeble batteries will come out with essentially their open source voltage, and you can ignore their internal resistance, which is what we want. You have to multiply this obviously by that scale factor by 1.103, but for our purposes bigger is better, so it doesn't really matter. Relative is fine. In here is a whole bunch of cells for various different chemistries that didn't work as well as these. Some of them are 200, 300 millivolts relative. So some of them are actually fairly good though. There's some nickel ones in here, there's some aluminium manganese ones, there's some ones that are made out of galvanized paint, sheridizing or galvanizing paint, aluminium paint, nickel paint, carbon conductive paint. I tried a whole bunch of different things, and those experiments are largely documented here, but there's some more ones that I haven't actually documented here. I tried adding potassium hydroxide on the hope that that would actually help. Don't do that, it ruins the cell. So you can see here if I put it in, this is a zinc manganese dioxide with a little bit of caustic potash mixed in. You can see 400-ish millivolts. This is a nickel manganese dioxide tripile that I made, and it's absolutely atrocious. This is about 80 volts, and look at it, it's enormous. Caustic potash or any kind of hydroxide, really, really bad idea. This cell is a zinc manganese dioxide tripile that I built. It has, I think, almost 100 plates in it, 100 cells in it. It used to put out 78 volts. It was really good, and then I thought I'd improve it by dunking it in ammonium chloride. Big mistake. This was laser cut in the printer, and I ended up shorting out the cell. I can't even disassemble it properly. It now puts out about 15 volts after that treatment, so really, really bad idea. And at the time, I actually thought that meant that ammonium chloride or zinc chloride or anything else treatment was not going to help a zinc manganese dioxide cell. But I persisted, and I did the experiment. So this is just plain old zinc. It's like 3 micron zinc dust or something mixed with a little gum arabic. This is manganese dioxide, also mixed with gum arabic on normal photocopier typing paper, American letter size. Okay, so we whack that in our little high impedance voltmeter. You can see we get about 850 millivolt, which is pretty reasonable, and it's certainly useful. This tripile was built using, those plates, 220, 240 of them, something like that. And as we saw earlier, it puts out a reasonable couple of hundred, 150, 170 volts, I can't remember, but anyway, pretty good voltage. It can blink a neon bulb, open circuit. So you can see here, I did something similar with some of those dodgier earlier nickel devices. Interesting phenomena. The leakage current of the neon bulb is voltage dependent. There's probably something radioactive in there, and if you unsolder this and just leave it open circuit, you can measure almost 220 volts out of this assembly here. But when you put the neon bulb across it and measure it again, it gets up to about 76 volts, 78 volts, which is about the breakdown voltage you'd expect. I haven't actually put this on the curve tracer yet, but I will put it on the curve tracer and analyze it a bit more. Also, light and dark affects it because, as you know, photoelectric effect. But basically, there's enough leakage that it's dragging down the voltage, and it's never getting to the point where it ionizes and discharges the capacitor. Except occasionally when you touch one side or the other, you'll trigger it. You must just give it enough voltage to start the avalanche. despite the leakage. And sometimes you can actually come up and touch it with the cell with another dry pile and push it over the edge, which is kind of cool, but not exactly what I wanted. This is pretty early, old technology now, and it's made with the laser cut ones, which we know have leakage and is generally a bad idea. I think if there was larger plate area, it would probably have enough current to overcome the leakage of the neon bulb. Certainly if you heat it up with a hot air blowgun, you get it up to about 60-70 degrees, it starts to blink like crazy. So there's a temperature dependence in batteries, like all batteries, and warming it up makes a big difference. Okay, so now we know what not to do, and we know that this is a reasonable direction to go in. Aluminium was promising, but aluminium manganese dioxide, aluminium carbon batteries have been researched for many years. There's problems in commercializing them. I think it's related to the oxide layer, and oxide production on aluminium tends to polarize the aluminium and passivate it, so that's not good for batteries. There's been attempts through changing the chemistry to get that to work better, but they never seem to be able to make a commercially usable battery, and the cost for zinc is not really worth it apparently, so we still have zinc-based batteries. Anyway, this is cell-added zinc sulfate too. So almost saturated solution of zinc sulfate. I just took these normal zinc manganese plates and I dampened the manganese side with the solution just as a quick hack, because it was easy to make a big sheet of it and then try different little swatches. So this was the first cell that sort of told me that I was getting on the right track. You can see it puts out almost a volt, which is significantly better. In fact, it's pretty close to a volt. Depends on the temperature again, humidity and temperature. Everything's quite variable. It's pretty damp in here today, so these cells are reading pretty low. Alright, this is zinc chloride. Now I expected this to work pretty well because, normal carbon zinc batteries use this kind of chemistry. And it does do pretty well. 1.2 volts, certainly the best that we've seen so far. But the cell is kind of floppy. The zinc chloride, I think, is sort of deliquescent, and it stores more moisture in the paper than we want, and it ends up being leaky and not as good. This is a mixture of zinc chloride and ammonium chloride, which is actually more like the chemistry of a carbon zinc battery. And it's a slight improvement, but not much. And this surprised me. This is ammonium chloride only. It was about a 80% saturated solution of ammonium chloride just painted on the surface. And depending on the quality of this one's been abused a bit, and it's of 1.3. I've got up to 1.4, 1.5 volts out of it. So if you multiply that by the 1.1, you're getting up around the open circuit voltage of a carbon zinc battery, which is kind of what you'd expect. There's no carbon in there, but there's manganese dioxide and zinc and ammonium chloride. So it's certainly looking pretty good. So this particular chemistry should work, as we saw with the other dry pile, which I've misplaced over here. With this guy, even that few cells had a reasonable output voltage, so I think I'll proceed with that particular chemistry. It's pretty easy to make. I'll just mix the ammonium chloride in with the manganese dioxide paste when I'm applying it, and I'll build this one out of the other 2 or 3 sheets that I have left of this material, and then I'll start making a much larger one. I might increase the area a bit to give me more current, and we can start doing electrostatic experiments with these things once they're in the kilovolt range, which, thanks to the more or less working metrology, we can actually do reasonable experiments with. Alrighty, hope that was interesting. It's kind of a long video, apologies, but yeah, I think you've got some useful tools if you want to kind of build your own dry piles. There's very few people out there experimenting with dry piles. I've seen 1 or 2 people on YouTube have videos about them. They're kind of cagey about how they built them. I wanted to be a bit more open about that. I didn't see any point in being secretive about it. There hasn't been a whole lot of research done since, I guess, a little bit after the Second World War, where they were used in night vision equipment. But basically they're just a big stack of thin batteries made using paper. And you don't need anything particularly fantastic to try and optimize it. These simple devices that I built, it's just JFET, some capacitors, there's nothing special. But leakage and humidity control and a whole bunch of other variables are very important. Temperature is a big variable, somewhat bigger than I actually thought it would be, but it's pretty significant. So a fair bit more research to go before I have something useful, but in the meantime I think I'm making pretty good progress. Alrighty, next time, bye.